Welcome to section 4.2, you mathletes. This is analyzing graphs of polynomial functions. Let's get right to business. Speaking of business, a banker models the expected value of a company in millions of dollars by using the formula V equals negative n to the fourth plus 12n third minus 46n squared plus 60n, where n is the number of years in business. No joke, this is what they actually do, and they get paid a lot of money to figure out what companies are going to get an increase in value and what companies are not. Graph the function and describe its key features over the relevant domain. They may use more sophisticated techniques than just polynomials, but this is like the Honors Algebra 2 version of what they actually do. So you can see here you got these input values and these output values, and don't do these by hand. Don't put I believe you that you could if given enough time, but it's just not going to be worth it because let's focus on other things. I think you could put 0, 1, 2, 3, 4, 5, 6, 7 into this entire polynomial and like take 5 to the fourth power and make it negative plus 12 times 5 to the third power minus 4. That's just a lot of computation. Don't do this by hand. Use a calculator. We're gonna focus our energies elsewhere. Anyway, you can graph the polynomial. You can see here 0, 0 gets plotted here, 1, 25 gets plotted up here, 2, 16 gets plotted here, and so forth. It goes all the way like that. And it's a word problem. So we're not really interested in any negative values for this particular kind of word problem. Once the business gets to zero value, then it's just going to be over. That's it for the business. And a negative x value doesn't make any sense either. So we're only looking at positive values. Positive n and positive v values here on this graph. I'm going to move my head over to the side. Boom. And then, so let's take a look. When you're looking at this graph and this equation, we can see these are the different things. If it's asking you to analyze a polynomial function, this is what we're looking for. This is an analysis. Degree is going to be degree here. The highest exponent is 4, and then we note that that's actually even. The leading coefficient is negative 1 because it's right here. Negative 1. There's an imaginary 1 in front of every variable if you want it, and that we note that that's negative. And the end behavior, well, there's not really any end behavior because it doesn't leave the graph. Like, it's a word problem, so it starts here and it ends here, and that's it. There's no more. However, if it weren't a word problem, then we would say that this continues down to negative infinity and this continues down to negative infinity. It just keeps on going. That's how it leaves the window if it weren't a word problem. And if it weren't a word problem, we'd say it's down, down end behavior. Just note that because it's good to practice. There's a relative maximum here and here. If you zoom in, this point and this point is it's the highest of its small little zoomed in region. It has a value of 25. That's an output v value of 25. And where is it exactly on the graph? Is when x equals 1 and 1, x equals 5. Remember, we describe where things are on a function based on their x values. And it's also it happens. It's not just the relative maximum; it's also the absolute maximum. The full-on maximum of the function is 25, and it occurs at 1 and 5. It does have a relative minimum here. If you zoom in, this value here of 9, this output of 9 is its own little. It's in its own little region, zoomed in region, ignoring everything else. It's 9, and where is it exactly? When x equals 3. The domain, well, it's a word problem. So if it weren't a word problem, this polynomial would have a domain of all real numbers. It just keeps on going, and as far as we want left and as far as we want right. And but because it's a word problem, we're restricting the domain. We're saying it starts here and it ends here, so it goes from 0 to 6. Again, the range also, because it's a word problem, we're not considering any negative values. The lowest y value is going to be 0, and the highest y value would be 25. If it weren't a word problem, we'd say it goes from negative infinity. There is no lowest y value. It goes from negative infinity up to a highest y value of 25. What are the x-intercepts? It intercepts the x-axis here at 0 and here at 6. And those also happen to be the zeros of the function. You plug in 0, you plug in 6 to this function, and you get out 0. What are the y-intercepts? Here, the y-intercept, it's not plural. There's only ever one y-intercept because it's a function. The y-intercept is 0, and you can see it intercepts the y-axis right here. There's only one. The maximum and minimum, well, we already said that this is the maximum over here. And because it's a word problem, we're going to say it has a minimum of 0 at 0 and 6. However, if it weren't a word problem, it would have no minimum. It would just keep on going down forever. And there is some symmetry here. There is some symmetry at x equals 3. You can see it's not. It has reflectional symmetry. This left half and this right half will fold over on each other. The mirror would be the line x equals 3. So it's reflectional symmetry. Let's take a look at this next one right here. I'm going to move my head, and there we go. Again, use a calculator. If you get something like this and they say analyze the polynomial function, don't do it by hand. I believe you that you could do it by hand, and we've practiced it enough, and we're just going to use calculators from here on out. So you plug in the function, you make a table, and then that table can help you make a graph if you need to. Boom. And it'll look like this. And so let's take a look. The degree is 3. That's the highest exponent, and we note that that's odd. The leading coefficient, I can't see it, but there's actually a 1 in front of this x cubed. And that's, so there it is. And because the polynomial is has an odd degree and a positive leading coefficient, we've memorized that it's going to be down up. And you can see on the graph, there's a down arrow that goes here and an up arrow that would go here, so down, up. Relative maximum, it does have a relative maximum right here, because in its own little zoomed in area, this is the highest point that it has. And it's the y value is going to be the output. The highest output is going to be 6.065, and where exactly is that going to occur? When x is equal to negative 1.869, approximately. It has a relative minimum over here, boom, at this y value and at this x value. And then what's the domain? Well, you can move left or right as far as you want to keep on plugging in x values and keep on churning out y values. So the domain is all real numbers, and even the range is all real numbers, because you can see you can go down as far as you want on a y value and go as high up as you want on the y values. What are the x-intercepts? There's 3 of them. And oh look, because the degree is 3, we can find, we happen to be able to find 3 x-intercepts. That's they occur at x equals negative 3, x equals 0, and x equals 1. There's the x-intercepts. They also happen to be the zeros of the function, the inputs that produce a 0 as an output. What's the y-intercept? I'll leave that to you. And what is the maximum or minimum? Well, there is no minimum. There is no absolute maximum, because the domain and range go to infinity and negative infinity. Is there any symmetry here? Yeah, I think, and maybe not at 0, 0, but if you rotate this around, if you flip your laptop upside down, then you could see that this is going to be rotationally symmetric. Maybe, and the center of rotation may be somewhere around here. And we'll leave it to a 12th grader in calculus to figure out exactly where it is, and you'll get there. But we'll just say vaguely that it's rotational right now. All right, polynomial of best fit models. Check this out. Backpacks. Let me move my head over here. Backpacks. The table shows U.S. backpack sales in millions of dollars according to the Travel Goods Association. Make a scatter plot and curve of best fit to show the trend over time, then determine the backpack sales in 2015. These are huge numbers, and sometimes it's going to be a lot easier to graph things if you're not graphing in huge numbers. So if the year of 2000, I'm going to let that represent 0. Basically, we're graphing years since the year 2000. And 2001 will just be a 1. 2013 here will be a 13. And then instead of graphing millions, I'm just going to go for billions, because the numbers are just that large. So there's 1.14 billions of dollars, and there's the table. Let's see. Boom. You can type all this into Desmos by typing table and adding all these numbers. And then here's what it would look like to find the actual curve. You type a y, a 1, and then that the approximately symbol right here. A x1 to the third, b x1 squared, c x1, and d. And we've told Desmos it's basically that we don't want to find we want to find the cubic curve. You can see the highest exponent is 3 that will fit this data the best. And we will allow Desmos to calculate the best A, B, C, and D values that we need in order to get it right. And it looks at all that data and says, well, it's not a great cubic curve, but this is the best I got. It gives it a rating of like 90.96, which is close to 1. 1 would be perfect. And then what you can do is you can trace this and go to 20. It wants to know about 2015. Boom. At x equals 15, this is what it would be. Anyway, I found it right here, and that is at $3.25 billion label. There it is. The best thing to do right now is to copy this command down. It's the hardest thing to type in, but it's basically saying look at the values of y1 and look at the values of x1, and there they are. And this is what we should. And you, Desmos, go ahead and calculate A, B, and C, and D, and there it is. Okay, so that's the end of what we need to know for the alex.com assignment, but I did want to say one more thing. And you might pose the question, well, Mr. Bergman, why do we have to use in this backpack problem a cubic regression? Like, why go x to the third? Well, why can't we just use a parabola, like we did for the strobe light parabola project? Or why not, why stop at 3? Why not go to the fourth power? Like, it could be ax to the fourth plus bx to the third plus cx squared plus dx plus, another constant like f. And so that's a great question, and not one that I'm going to give. I do want to answer that question now, but you're not going to need to know that information for the alex.com assignment. You will need to know that information for about 4 lessons when we finish chapter 4 and we do the chapter 4 project. And I do want to talk about it right now because it's kind of applicable. So over here, and in order to do that, we have to borrow some ideas from geometry. So what I've got here is I've got a picture of a solid or some sort of thing from geometry, and then you can see what the shape it is, and then we've got formulas from geometry. So for example, if instead of backpacks you had a whole bunch of circles, for example, and you had a whole bunch of data relating the circumference to the diameter, and you wanted to relate them all together, you would have to think about the circle and say, this formula right here, circle is equal to pi d. The highest exponent on here, there's a whole bunch of exponents, but the highest exponent here is really 1. It's unwritten, but on d, there's an unwritten exponent of 1. So therefore, you can see the degree of the formula is 1. It's linear. And thinking about it, stepping back, even not knowing anything about exponents, the circumference is a one-dimensional phenomenon. Circumference is measured in meters or feet, not meters squared or feet squared. It's a linear relationship between d and c, and so therefore, if you had a whole bunch of circumferences and diameters, as you had backpack sales in years, then the regression you wouldn't use a cubic regression for that. You would use a linear one because it's linear in nature and the exponent is 1. So here the regression would be y1 is approximately, or regression symbol, m times x1 plus b. You would ask Desmos to find the best possible m value and b value for the data that you have. However, if you had still thinking about a circle, you can also have areas. Let's say the data that you had, not a table like this and backpacks in years, but let's say you had a whole bunch of circles and you had a whole bunch of radii and areas paired together. The relationship between those two is not linear. You can see the exponent is 2. It's quadratic because the degree is 2. And stepping back and thinking about it, area is a 2-dimensional phenomenon. You measure area in feet squared and meters squared, not feet or feet cubed, but just feet squared, square feet. And so the regression you would need in order to relate these two would be y1 is approximately ax1 squared plus bx1 plus c. Just a general, every quadratic can be modeled like this for some values of a, b, and c. Moving on, surface area is here. You can see the surface area, the formula for the surface area of a rectangular prism is 2 times length width. Like the very front and back faces are going to be length and width times 2. And then the surface area 2HL plus 2HW. and surface area itself is measured. It's a kind of area. So in nature, you could already guess that it's going to be quadratic. But even if you didn't know that the rectangular prism, the surface area of a rectangular prism was two-dimensional in nature because it's an area, you would be able to look at the formula and know that the length has an exponent of 1, the width has an exponent of 1, and so 1 plus 1 for this entire term is 2. This formula is quadratic, and so you would need, if you had a whole bunch of lengths and widths and heights and surface areas, you would somehow need to model that with y1 is approximately ax1 squared plus bx1 plus c, because it's quadratic in nature. Or let's say if the surface area was changing over time, you could say the x1 value would be like over the year, like you had a rectangular prism, a singular rectangular prism that was changing throughout the years, for example, and the surface area was increasing. You would have to say that the x1 values would be time, and the surface areas would be y1, and relate them with a quadratic regression. Here, or let's say we had a rectangular prism and you were tracking its volume. Like over time, the x1 values were time and the y1 values were volumes. That would be a cubic regression, because volume is in nature three-dimensional. You say cubic centimeters or cubic feet or cubic yards. And so therefore the time would be x1 here, and then the y values would be here, the volumes, and you would need some sort of cubic regression to do it, as we saw the same exact thing here. I know these boxes are kind of small on your packets, so feel free to like write on the side or find somewhere else, or just write the same as above, or whatever you need to do to make it fit, make sense to you. Cylinder. Here's the formula for area of a cylinder, and even thinking about it geometrically, area is two-dimensional. But even if you didn't know that and you just had a formula that you didn't really understand, you could still look at this and say, oh, the highest exponent here is 2. And even over here on this term has an exponent of 2, because r has 1 and h has 1, and you add the two together and you get 2. Pi is actually not, doesn't add to the degree of the polynomial, because pi is just a number, same as 2. So it's not really part of the variable. You look at the variables. R is 1, H is 1. You add them together. Volume of the cylinder is three-dimensional, and even if you didn't know that, R squared, so you see the 2 here and you see the 1 here, 2 plus 1 is 3. And so that would be a cubic, you would know that the volume is a cubic phenomenon, and you'd have to use a cubic regression to do it. If you had data on a sphere that were expanding, say, like someone was blowing up a bubble over time, and you had not years, but maybe over the course of a couple seconds, at time equals 0 is this, and then you're blowing it up over the course of 10 seconds or maybe 15 seconds, and you track all of the volumes, you could say that here the radius is increasing with time, and the volume is here, and so that it would be cubic. You would use knowing that volume is a three-dimensional phenomenon, you can go right to the 3 cubic, but even if you didn't, the formula has an exponent of 3, so therefore the regression would be here. And lastly, surface area, same idea, squared to quadratic. You don't have to, I know there's a lot of text characters over here in this really small, tiny little box, and difficult for you to take notes, so do the very best you can, and we'll sort it out tomorrow in class. So thanks for watching. Thanks for paying attention. Save all, like I said earlier, save all these ideas right here in this table. Not for the alex.com, you won't see it, but for the project coming up at the end of chapter 4, you will, and we'll come back to it later. Like I said, thanks for paying attention. Thanks for taking good notes and thinking critically, and bring your questions to class, and we'll talk about them tomorrow. Take care.